And we'll move to the starting and charging systems. The starting system is responsible for getting the engine started. When the ignition key is turned to the start position, a small amount of current flows from the battery to a solenoid or relay. This activates the solenoid or relay and closes another electrical circuit that allows full battery voltage to reach the starter motor. The starter motor then rotates the flywheel mounted on the rear of the crankshaft. As the crankshaft turns, the pistons move through their strokes at the correct time for each cylinder. The ignition system provides the spark to ignite the air-fuel mixture. If good combustion takes place, the engine will now rotate on its own without the need of the starter motor. The ignition key is now allowed to return to the on position. From this point on, the engine will continue to run until the ignition key is turned off. The electrical power of the engine and the rest of the car comes from the car's battery. The battery is especially important for the operation of the starting system. While the starter is rotating the crankshaft, it uses a lot of electricity. This tends to lower the amount of power in the battery. Therefore, a system is needed to recharge the battery so that engine starts can be made in the future. The charging system is designed to recharge and maintain the battery states of a charge. Also to provide electrical power for the ignition system, air conditioner, heater, lights, radio, and all electrical accessories when the engine is running. The charging system includes an AC generator, voltage regulator, indicator light, and the necessary wiring, rotated by the engine's crankshaft through a drive belt. The AC generator converts mechanical energy into electrical energy. The AC is converted into direct current, DC, within the alternator. When the output of electrical current from the charging system flows back to the battery is being charged, and when the current flows out of the battery is said to be discharging. And we'll move right now to the electronic engine controls. Nearly all vehicles on the road have an electronic engine control system. This is a system comprised of many electronic and electromechanical parts. The system is designed to continuously monitor the operation of the engine and to make adjustments that will cause the engine to run more efficiently. Electronic engine control systems have dramatically improved fuel mileage, engine performance, and drivability, and have greatly reduced exhaust emissions. Electronic control systems have three main types of components: input sensors, a computer, and output devices. The computer analyzes data from the input sensors. Then, based on the inputs and the instruction held in its memory, the computer directs the output devices to make the necessary changes in the operation of some engine systems. So electronic control systems have fewer moving parts than old-style mechanical and vacuum controls. Therefore, the engine and other support systems can maintain their collaboration almost indefinitely. As an added advantage, an electronic control system is very flexible. Because it uses computers, it can be programmed to meet a variety of vehicle engine combinations or collaborations. Critical quantities that determine an engine performance can be changed easily by changing data that is stored in computer's memory. Also, we have the onboard diagnostics. Today's engine control system are onboard diagnostic second generation systems, or OBD the second. These systems were developed to ensure proper emission control system operation for the vehicle's lifetime by monitoring emission-related components and systems for deterioration and malfunction. This monitoring includes also a check of the tank ventilation system for vapor leaks. The OBD system consists of the engine and the transmission control modules and their sensors and actuators along with the diagnostic software. The computer can detect system problems even before the driver notices a drivability problem, because many problems that affect emissions can be electrical or even chemical in nature. When the OBD system determines that problems exist, a corresponding diagnostic trouble code is stored in the computer's memory. The computer also illuminates a yellow dashboard light indicating a check engine or service engine soon, or displays an engine symbol. This light informs the driver of the need for service, not of the need to stop the vehicle. A blinking or flashing dashboard lamp indicates a rather severe level of engine misfire. When this occurs, the driver should reduce engine speed and load and have the vehicle serviced as soon as possible. After the problem has been fixed, the dashboard lamp will turn off. Also, another system that we have is the heating and air conditioning systems. And let's start with the heating systems. To meet federal safety standards, all vehicles must be equipped with passenger compartment heating and windshield defrosting systems. The main components of an automotive heating system are the heater core, the heater control valve, the blower motor, and the fan, and the heater and defroster ducts. The heating system works with the engine's cooling system and converts the heat from the coolant circulating inside the engine to hot air, which is blown into passenger compartment. A heater hose transfers hot coolant from the engine to the heater control valves and then to the heater core inlet. As the coolant circulates through the core, heat is transferred from coolant to the tubes and fins of the core. Air blown through the core by the blower motor and fan then picks up heat from the surface of the core and transfers it into passenger compartment. After giving up its heat, the coolant is then pumped out through the heater core outlet, where it's turned to the engine's cooling system to be heated again. Transferring heated air from the heater core to the passenger compartment is the job of the heater and defroster ducts. The ducts are typically part of a large plastic shell that connects to the necessary inside and outside vents. Contained inside the duct are also the doors required to direct air to the floor, dash, and windshield. Also, we have the air conditioning systems. An air conditioning system, or AC, is designed to pump heat from one point to another. In an automotive AC system, heat is removed from the passenger compartment and moved to the outside of the vehicle. The substances used to remove heat from the inside of the vehicle is called the refrigerant. To understand how a refrigerant is used to cool the interior of a vehicle, the effects of pressure and temperature on it must be first understood. If the pressure of the refrigerant is high, so its temperature. Likewise, if the pressure is low, so is its temperature. Therefore, changing its pressure can change the refrigerant's temperature. To absorb heat, the temperature and the pressure of the refrigerant are kept low. To get rid of the heat, the temperature and the pressure are high. As the refrigerant absorbs heat, it evaporates or changes from liquid to vapor. As it dissipates heat, it condenses and changes from a vapor to a liquid. These two changes of state occur continuously as the refrigerant circulates through the system. An AC system is a closed pressurized system. It consists of a compressor, condenser, receiver, dryer or accumulator, expansion valve or orifice tube, and an evaporator. The best way to understand the purpose of the components is to divide the system into two sides, the high side and low side. High side refers to the side of the system that is under high pressure and high temperature. Low side refers to the low pressure and low temperature side. So one of the components of the system is the compressor. The compressor separates the high and low sides of the system. Its primary purpose is to draw the low pressure and low temperature vapor from the evaporator and compress this vapor into high temperature, high pressure vapor. The secondary purpose of the compressor is to circulate or pump the refrigerant through the system. The compressor is located on the engine and is driven by the engine's crankshaft via drive belt. Compressors are equipped with an electromagnetic clutch as part of the compressor pulley assembly. The clutch is designed to engage the pulley to the compressor shaft when the clutch coil is energized. When the clutch is not engaged, the compressor shaft doesn't rotate and the pulley freewheels. The clutch provides a way for turning the compressor on or off. Also, another part that we have is the condenser. The condenser consists of a cold tubing mounted in a series of thin cooling fins to provide maximum heat transfer in a minimum amount of space. The condenser is normally mounted just in front of the vehicle radiator. It receives the full flow from air from the movement of the vehicle or airflow from the radiator fan when the vehicle is standing still. The condenser condenses or liquefies the high pressure, high temperature vapor coming from compressor. To do so, it must give up its heat. Very hot high pressure refrigerant vapor enters the inlet at the top of the condenser. And as the hot vapor passes down through the condenser coils, heat moves from the refrigerant into the cooler air that flows across the coils and fins. This loss of heat causes the refrigerant to change from high pressure hot vapor to high pressure warm liquid. The high pressure warm liquid flows from the bottom of the condenser to the receiver or to the refrigerant metering device if an accumulator is used. So what is the receiver or dryer? The receiver or dryer is a storage tank for the liquid refrigerant from the condenser. The refrigerant flows into the receiver tank, which contains a bag of desiccant. What is a desiccant? It's a moisture-absorbing material. The desiccant absorbs unwanted water and moisture in the refrigerant. Also, another part that we have is the accumulator. Most late model systems have an accumulator rather than the receiver or dryer. The accumulator is connected into the low side of the outlet of the evaporator. The accumulator contains a desiccant and is designed to store excess refrigerant. If liquid refrigerant flows out of the evaporator, it will be collected by and stored in the accumulator. The main purpose of an accumulator is to prevent liquid from entering the compressor. Also, another important part that we have is the thermostatic expansion valve or orifice tube. The refrigerant flow to the evaporator must be controlled to obtain maximum cooling while ensuring complete evaporation of the liquid refrigerant within the evaporator. This is the job of the thermostatic expansion valve or TEV. Some people they abbreviate it as TXV, or a fixed orifice tube. The TEV is mounted at the inlet to the evaporator and separates the high pressure side of the system from low pressure side. The TEV regulates the refrigerant flow to the evaporator by balancing the inlet flow to the outlet temperature. Like the TEV, the orifice tube is the dividing point between the high and low pressure sides of the system. However, its metering or flow rate control doesn't depend on comparing evaporator pressure and temperature. its fixed orifice. The flow rate is determined by pressure difference across the orifice and by the additional cooling of the refrigerant in the bottom of the condenser after it has changed from vapor to liquid. Also, we have the evaporator. The evaporator, like the condenser, consists of a refrigerant coil mounted in a series of thin cooling fins. The evaporator is usually located beneath the dashboard or instrument panel. The low pressure, low temperature liquid refrigerant from the TEV or orifice tube enters the evaporator as a spray. The heat at the evaporator causes the refrigerant to boil and change into a vapor. The transfer of heat from the evaporator to the refrigerant causes the evaporator to get cold. Because hot air always moves toward cold air, the hot air from inside the vehicle moves across the evaporator. As the process of heat loss from the air to the evaporator core surface is taken place, any moisture in the air condenses on the outside of the evaporator core and is drained off as a water. This dehumidification of air adds to passenger comfort. Also, we have the refrigerant lines. There are three major refrigerant lines. Suction lines are located between the outlet side of the evaporator and the inlet side or suction side of the compressor. They carry the low pressure, low temperature vapor to the compressor. The discharge or high pressure line connects the compressor to the condenser. The liquid lines connect the condenser to the receiver or dryer and the receiver or dryer to the inlet side of the expansion valve. Through these lines, the refrigerant travels in its path from a gas state to a liquid state, and then to the inlet side of the expansion valve, where it vaporizes at the evaporator.